Hello and welcome to our course, Multimedia Applications and Virtual Reality. In this session, we will detail the VR application domains and technical constraints. Let's now ask the big question. When does a computer solution truly qualify as virtual reality? First, VR becomes relevant when the system builds or represents a 3D spatial environment. Here, the problem itself is modeled in 3 dimensions, not simply through data or flat 2D interfaces. Objects and entities have real spatial properties, their position, orientation, scale, and behavior in a simulated space. And importantly, the user's viewpoint can be placed inside that environment. For instance, instead of studying ergonomics through diagrams or tables, imagine simulating an entire factory in 3D, walking through it, and analyzing movement directly within the space. Second, the solution must involve user-centered immersion. The user is no longer an outside observer. They become part of the model itself. The system continuously calculates visuals and feedback relative to the user's position and orientation. That's where head tracking and viewpoint control come in. The goal is to make the user feel present inside the system, not just watching it on a screen. Think of a training tool where an operator can look freely around a virtual cockpit instead of viewing a fixed image on a monitor. Third, interaction must be continuous and spatial. The user doesn't simply click buttons. They act directly within the simulated world through gestures, movements, or devices that correspond to real actions. Every gesture affects the virtual environment in real time, producing visual, auditory, or haptic feedback. For example, imagine grabbing and moving a virtual object to feel its weight or test its balance. That's authentic VR interaction. Fourth, the core of the system is a simulation, not just a visualization. True VR is dynamic. It reproduces physics, motion, and procedural changes as they happen. It's not a static 3D model or a pre-rendered animation. It's a living system that responds to your actions according to its internal laws or scenarios. For instance, simulating airflow around an aircraft in VR goes beyond just showing its shape. It lets you experience how it behaves. Fifth, the objective of VR is experiential understanding or skill transfer. It's not about observing, it's about experiencing and learning through immersion. That includes training like pilot or surgical simulation, design evaluation such as architectural walkthroughs, and even empathy or therapeutic applications like exposure therapy or cultural immersion. In short, it's about feeling what it's like to operate a crane, not just reading the manual. Finally, a true VR system integrates a real-time feedback loop. Every user action is instantly captured by sensors, processed by the system, and reflected in the environment, creating a seamless action-reaction cycle. This continuous loop, user action to sensor input, to environment update, to display output, transforms the computer from a static tool into an interactive experiential medium. For example, when you turn your head, the scene must update immediately without delay or predefined camera paths. That's the true hallmark of real-time VR. Let's now look at where virtual reality actually finds its applications. In practice, VR applications fall into 2 major families: art and attraction, and engineering. These 2 families correspond to 2 very different philosophies of use, one driven by imagination and emotion, the other by precision and simulation. Art and attraction. Imagination, symbolism, and synthesis. This first family explores the creative, cultural, and emotional dimensions of VR. Here, the goal isn't physical accuracy, it's about experience, symbolism, and aesthetic immersion. Virtual reality becomes a medium of expression and feeling. Entertainment and gaming are the most visible examples. VR transforms traditional games into living worlds, first-person adventures, immersive role-playing, or full-body esports experiences.
Even theme parks use VR for attractions that blend storytelling with physical movement. In culture and heritage, VR opens the doors of virtual museums and art galleries, allowing 3D navigation and guided tours through reconstructed ancient sites and monuments. It even brings history and mythology to life through immersive storytelling. The performing arts also embrace VR, with theater and dance that can be experienced from within the stage itself. Audiences can attend 360-degree concerts or explore virtual choreographies designed for education and creation. In cinema and visual media, directors now use VR for 360-degree immersive films, virtual film sets, and interactive artistic installations, redefining how we watch and feel stories. Finally, VR is entering wellness, tourism, and emotional experiences. It allows people to travel virtually to distant or inaccessible places, to meditate or relax in serene digital environments, and even to express themselves artistically through virtual painting or sculpture, a form of digital art therapy. Engineering, real, reproduction, and simulation. The second family of VR applications is much more technical. Here, VR is used for precision, performance, and problem-solving. It focuses on realistic modeling, data-driven reproduction, and interactive simulations of real systems. In industry and manufacturing, VR supports virtual prototyping, enabling engineers to design and test before physical production. It's also used for assembly and maintenance training, helping workers practice safely in realistic conditions. And for ergonomics and safety, it allows full-scale evaluation of workplace setups. In transport and mobility, VR provides driving and flight simulators for pilots and drivers, supports vehicle design validation, and extends to maritime and even space operations simulations. In medicine and healthcare, VR plays a transformative role, from surgical simulators that train doctors to rehabilitation environments for physical or cognitive recovery, and even therapy for phobias and PTSD. Patients can explore 3D anatomy to better understand their own conditions. Architecture and construction benefit from virtual walkthroughs long before a single wall is built. Urban planners can simulate lighting, noise, and traffic, while architects collaborate in shared VR environments to refine designs. In science and research, VR is an invaluable tool for visualizing complex data, from molecules to galaxies. It enables experimental simulations in physics, biology, or engineering, and supports virtual laboratories that make remote scientific collaboration possible. Finally, training and learning deserve special mention. VR provides hands-on learning experiences even in remote or hazardous environments. It simplifies the explanation of complex concepts through immersive 3D demonstrations and allows safe training in high-risk or inaccessible situations, from firefighting to space missions. So, whether it's for artistic creation or scientific precision, virtual reality has become a powerful bridge between imagination and realism, a technology that lets us not only see information, but live it.
The virtuality continuum, proposed by Milgram and Kishino in 1994, describes how we move from the real world to a fully virtual one. It begins with the real environment, where everything we perceive comes from natural, physical reality. Then, augmented reality adds virtual elements, like data or 3D objects, directly into the real world. At the center, mixed reality blends both worlds so that real and virtual objects interact dynamically. Moving further, augmented virtuality is mostly virtual, but still integrates real-world elements, such as live video or real objects. And finally, virtual reality
immerses the user completely in a synthetic environment where all perception is virtual. Together, these stages form a seamless spectrum from real to virtual, which we now refer to as extended reality, or XR. XR is the umbrella term that unites AR, MR, and VR, representing the full range of immersive experiences where the physical and the digital meet.
When we talk about developing multimedia or mixed and augmented reality applications, often called MMAs, we're really talking about the meeting point between creativity and engineering precision. These systems are not only artistic or interactive creations, they are complex ecosystems that must manage how information is represented, processed, transmitted, and ultimately experienced by the user. In other words, the technical and functional constraints are not optional. They define the very structure and behavior of the application. From a technical perspective, every MMA is built upon several perceptual dimensions. The textual dimension deals with symbols and written language, relying on encoding systems like Unicode to ensure that text displays consistently across platforms. The visual dimension concerns images and 3D models, where technologies such as modeling, rendering, and computer graphics bring virtual spaces to life. The auditory dimension governs sound, speech, music, and effects, processed through signal encoding to match the tone and rhythm of the experience. Then we have the haptic dimension, which introduces touch and physical feedback, using physics-based simulation to reproduce sensations like pressure, vibration, or resistance. Some applications even explore the olfactory and gustatory dimensions, working to reproduce smells and tastes through sensory chemistry, an area still in active development. And finally, the hypermedia dimension connects everything together, structuring relationships between content through markup languages like HTML or XML. Each of these dimensions requires its own technical expertise, but the real challenge of multimedia design lies in synchronization, making sure that text, visuals, sounds, and tactile feedback merge into one coherent, seamless experience. That's the essence of a well-designed MMA, a symphony of senses orchestrated by technology. Beyond representation, these systems must also be defined by their functional specifications, how they behave, communicate, and react to users. Interactivity lies at the core of this functionality. Systems often rely on artificial intelligence and cognitive psychology to anticipate user behavior, adapt content dynamically, and respond to unexpected actions. Broadcasting, meanwhile, defines how data is delivered, whether locally through client-server systems or across distributed cloud networks. Security and authenticity are equally essential. They ensure that digital content remains trustworthy and protected through techniques such as encryption, watermarking, and digital rights management. At the same time, system goals must be clear. Some applications require real-time execution, such as simulators or collaborative VR environments, while others operate on demand, prioritizing efficient data retrieval and storage optimization. Rendering transforms data into immersive output through advanced visualization pipelines, and interfacing ensures that the technology remains intuitive and accessible, aligning with the principles of human-computer interaction and ergonomics. Ultimately, the technical specifications define what the system can represent, while the functional specifications define what the system can do. Together, they determine whether a multimedia or mixed reality experience is not only visually impressive, but also intelligent, reliable, and truly centered on the human experience. To conclude this part, let's remember that a multimedia or mixed or augmented reality application, what we call an MMA, is not just a technological product. It's a complete ecosystem where several worlds meet and interact. It brings together sensory representation, what the user perceives, interactive logic, how the system reacts to them, technical efficiency, how smoothly, securely, and responsively it runs, and finally, human factors, how intuitive, comfortable, and meaningful the whole experience feels. In short, an MMA must integrate multiple sensory inputs and outputs, maintain security and ethical integrity, and ensure both interactivity and performance at every level. To achieve this balance, we need a cross-disciplinary approach. That means collaboration between experts in computer science for graphics, artificial intelligence, and signal processing, engineering for mechanics, electronics, and physics, cognitive science to understand perception and usability, and finally, ethics and law to safeguard security, privacy, and intellectual property. That's what makes multimedia and mixed reality so fascinating. It's not only about building systems, it's about building experiences where technology and humanity meet in real time.